Hello, hello. Welcome everyone. Okay, sorry, my last class went over because I had technical issues with my microphone at the beginning of last class. So those technical issues have been fixed, but now I can't hear any sound. So if someone chats in voice, I can't hear you at all. So we do have a TA here. Say hi to everyone. And she is going to be handling chat. Feel free to ask questions in chat, and et cetera, et cetera, et cetera. Any questions, comments? Oh, I'm Scott Grizzard, and this is Calculus from the University of South Florida, remote. So I'm supposed to say that every time. Any questions, comments, issues, suggestions, thoughts before we get started? Okay, so here's roughly what we're going to do schedule-wise. And make sure that you're in the proper chat. The chat channel is 20 on Discord is 2020-04-06, the 11 a.m. I see 2 messages there. I do see people in voice chat, which is awesome. I'm so glad you're here. Welcome, welcome, welcome. And anyone visiting from outside, welcome too. I'm glad you made it. Okay, so today what we're going to do, last time we went over optimization. Today's plan is to go over L'Hopital's rule. Tomorrow, now I would do this on Wednesday during the problem set, except that people were asking for more optimization problems. And I want to talk about a thing that's not on the test. I mean, you can use it on the test. It's another way to do optimization problems, but it's totally optional. So tomorrow afternoon at 5 p.m., I'm going to do a second lecture, kind of Twitch thing with more optimization problems. I'm going to go through one of the ones that's going to be on the problem set, and another way to do them. Now you can come, you can not come, watch the video, don't watch the video. That's entirely up to you. As I said, it's completely optional. But people were asking for more examples of optimization problems, so I'm going to be doing that. Other news. So Wednesday, of course, I'm doing the class. We're going to go over the quiz. After we go over the quiz, we'll go over something called the maximum function, which is part of this section. And then we're going to go over I'm sorry. Then we're going to go over the area under the curve function, and we'll begin module 4 with that. So the maximum function is something that's technically in module 3, but no one ever gets to it. No one even covers it except me. But I actually think it works. It's helpful because then it helps with the AEC function. And then at Wednesday, 5 p.m., we're going to do test review. And then at Thursday at 7 p.m., there's another test review. Let me say a couple things real fast about the test before we get started. So the final version of the test, at least what they say is the final version of the test is done. No promises into what that actually ends up being. But you'll see on here on the test, for the test on Saturday, you need to print this answer sheet. You can either print it or you can trace it. If you absolutely cannot get it printed, I highly advise you printing it. If you can't get it printed, send me your address on Discord as a direct message or an email today. And I mean, if you absolutely can't get it printed, I will print it myself and mail it to you. Okay, I want you to have the actual answer sheet. So if you absolutely, now I'll be paying for that myself. So if you absolutely cannot get it printed, send me an email and I'll mail you one. Anyway, but that's the test 3 answer sheet. Now, if you look on here, I've also got a whole bunch of other stuff on here. I've got the notice about the test review sessions, the bootleg, the official test review problems. So you got the bootleg here. Now, if I click on the official test review, you'll see something that I did here that was pretty intense. I went down and I went through the bootleg. First of all, of course, I've added examples here, like I normally do. So if you look at this one has examples from each section. And then what I did is I went through the quizzes, of course, and I put the quiz information on here, which problems were relevant from the quiz. And then I went through the bootleg and I talked about each problem on the bootleg and what it looks like relative to the test. Now, there's one other thing on the bootleg that happened, is that a bunch of material got cut. So I made a list of all of the proofs and theorems from the module, and this was a suggestion by one of your classmates, whose name, of course, I can't mention on Discord, on Twitch. But I made a list of every single theorem that we've gone over, since there were so many. And what I did was I told you where it was in the book, okay? If we proved it in class, if it was proved in the book, and where it is proved in the book, if it is proved in the book, then whether or not you have to state it on the test, and by state, I mean the first question may read, state Weierstrass's extreme value theorem, or state Fermat's stationary point theorem, or state Rolle's theorem, or state Cauchy's mean value theorem. Those are all things that might wind up as statements on the test. Whether or not you need to use it for the test, and then whether or not you need to prove it on the test. Now notice here that these things where they said cut. So that thing where I made you do Rolle's theorem in a quiz, because that was one of the options on the test. Since that happened, that proof has been cut. The other proofs that have been cut are Cauchy's mean value theorem, the proof, the derivatives determine the shape, the proof, and the increasing decreasing test, the proof. So those 4 proofs, okay? Just the proofs, not the statement of the problems, not anything. Those 4 proofs have been cut. You don't have to prove them verbatim. Instead, they've been replaced with a true-false question. That's what we'll be talking about today. Now, they're still on the bootleg. I put on the bootleg that they'd been cut, but they are on the bootleg, and some of them are really cool. So the ones that are on the bootleg, there are proofs on the test, okay? There's 2. One of them is a proof question, a problem, for which you use mean value theorem or Rolle's theorem or one of the theorems to do, right? So you prove that something doesn't exist or can't exist or that sort of thing, okay? That's on there. And there's still you notice how here, right? But that's a proof problem. That's not really a proof verbatim problem. And then notice there are 3 proofs still on the test. There's one proof that will ask you you'll be asked to prove one of these. I get to pick which one you're proving. So you have to know all 3. Now, really, you only have to know 2 of them because arc cosine and arc sine are the exact same proof. So that question is asked. So 2 of these are on the bootleg. Arc sine and arc tan are on the bootleg. Arc cosine was on a quiz. So that proof is still on the test. One of those 3 is still on the test. And one will be on the makeup and one will be on the regular version. Okay? The thing that got cut, and there's still a problem that asks you to prove something. Can this function exist or not? Okay? But the problems that got cut, the long proofs, these 4 long proofs all got cut. Okay? So I'm just going to walk you through that. They're still on the bootleg. I like them on the bootleg. But you can, they're not on the test itself. There's an official practice test. Of course, the peer leading test review is up. And the bootleg, of course, is up. And one of the things I did on the bootleg, if you look at the practice test, I told you, hey, this is similar on the bootleg, this is similar on the bootleg, this is similar on the bootleg. So I told you what the levels of difficulty were. Are there any questions about that? Questions, comments, issues, suggestions, thoughts? Okay. So that's all I'm going to mention about the test. I'm going to mention more about the test on. I'll mention more about the test on the test review sessions. Okay. So what's going on here? The last time we talked about optimization. Today we're going to go over L'Hopital's rule. Yes, that's on the test. Tuesday, tomorrow, I'm going to go over more optimization problems since people were requesting it. I'll also show you another way of doing optimization problems that used to be part of the main part of the class. I'm kind of it out to spend more time because, I'm discovering that I get through less on the Twitch than I did in regular lecture because of technical issues and things like that. So those things will be covered separately. They're not on the test, but you can use it on the test. There's a rather slick way of doing some of these optimization problems. On Wednesday during class, I'm going to start the module 4. I'm going to start with what's called the maximum function, which is technically part of Module 3. And then we'll talk about the area under the curve function. Wednesday at 5 p.m. test review, Thursday at 7 p.m. test review. Those will not be recorded. Those will be on Discord, not on Twitch. So on Twitch tomorrow is 5 p.m. optional, more problems. Wednesday and Thursday tomorrow night, not on Twitch, on Discord. Of course, the other one's on Discord as well. Any questions about that? Okay. Let's slip on over here. Let's go to the quiz. Okay. Any questions, comments, issues, suggestions, thoughts? Okay. So anyway, for the quiz, just out of curiosity, how do we feel about this quiz, 1 to 5? So 1 to 5 overall, how do we feel about the quiz? Okay. Just before we're talking about it. Okay. So, okay. So let's talk about it. This one's a little hard. It's actually not that much harder than the one we did, but it's got a distraction in it. And the distraction is this maximum here. Now, remember when I said, think about what costs money, okay? This 180 feet doesn't cost money. It's not part of the constraint. It's something that's about an endpoint, but it's not technically the thing that costs money. The thing that costs money is fence, okay? And that's the key to remember, is you want to look for the things that cost money, okay? So what I'm going to do is I'm going to set it up here. And when I read this, I'll set it up as I read it here. So no fencing is needed along. So I want to fence north of my barn. So I've got a barn here, and I want an enclosed area north of the barn. Okay. No fencing is needed on the barn. In other words, this side is free. And on the west side, this side, my neighbor and I are going to share the cost, right? Mexico may be paying for the whole part of this wall, but Canada's only splitting half and half with this stuff, right? We're going half and half on this side. This side I have to pay for myself, and this side I have to pay for myself. Those each are $20 a foot. And this side, because I'm paying half the cost, is only $10 a foot to me. Okay? How do we feel about that setup, 1 to 5? Okay. So again, the thing I want to keep in my brain is the question, what costs money? Okay? On peer leading, what costs money? Tape. Okay? Now, my constraint was just in terms of tape, but every foot of tape cost me a foot of tape. Okay? It cost me money. What costs money on the water bottle problem? Did you guys get to the water bottle problem on Friday? Water bottle problem? Anyway, the water bottle problem. What costs money? Aluminum. Okay? So I want to minimize the cost of the aluminum, right? The production of the water bottle, given a fixed volume. And aluminum costs money. So I wanted to make a more efficient water bottle. Okay? So those were the ideas. That's the big idea for figuring out what the constraint should be. Ask yourself the question, what costs money? Now here, I've got my constraint, right? My cost equals 10 times this side, 20 times this side, 20 times this side, and 0 times that side. And that whole thing has to add up to 6,000. Okay? That's my constraint. The thing I'm trying to find is area, which is length times width. That's the thing I'm trying to maximize given this constraint. 1 to 5, how do we feel about that? What I'm trying to maximize given what's my constraint? Okay. So what I'm going to do is I'm going to take these two equations and I'm going to combine them into one equation. Okay. So here I solved for W, and then I plugged W into this equation here, and I wound up with 300L minus 3 halves L squared when it was all said and done, after I multiplied out the L. Now I'm going to take the derivative and I'm going to set it equal to 0. Okay? So if I take the derivative and set it equal to 0, the derivative of this thing's 300 minus 3L. That equals 0. That immediately gets me that L equals 100 feet. How do we feel about that, 1 to 5? Once I get the area equation, taking the derivative, setting it equal to 0, and solving for L. Okay. Now, while I'm here, and I could have done this later, but while I'm here, I'm going to check out what this 100 feet means. Okay? I'm going to take the second derivative. I'm going to set it. I'm going to take the second derivative and see what the concavity is while I'm at it. Now, again, I could do this later. I could do this earlier. I could do it whenever. The fact is, I just took the first derivative. I've got the first derivative in front of me. I took the second derivative. And when I took the second derivative, I wound up with negative 3, and that's less than 0. So this function is concave down everywhere, making L a max. L equals 100 a max. Now, I'm going to go back and I'm going to look at my problem. I had this weird oak tree condition, right? That meant that the west side of the fence, this was an L, the west side of this fence, it can only be 180 feet. Does that matter? Well, no. Why doesn't it matter? Because 100 is less than 180. If I took 180 feet, 180 feet as my L, I would wind up with something smaller. How do I know? Well, because the function is concave up. Concave down. Right? So I know my max, if I do this little concave down function, I know my max is right here, right? Right where the derivative equals 0. Why? Because the function's concave down. Okay? So how do we feel about that, 1 to 5? This endpoint business doesn't matter for this case. Okay. There are other ways to do this. I could have taken the area, right? Here I've got one critical value. I could have taken the area when L was 0, and I could have taken the area when L was 180 and figured out what those were, and then said, oh, well, if L is 100, my total area is bigger. So I could have checked endpoints. I could have also done a first derivative test. Any one of those three would have worked. There were 3 ways to check this. Okay? 3 ways. Everyone on board with the 3 ways to check this? 1 to 5, how do we feel about that? There were 3 ways to check this thing. I hate this glove. Maybe I should get a hole. Of course, then if I got a hole one, I couldn't move the thing. Okay. Now, I've got an L, so I'm going to solve for a W and an A, and I do that, and I wind up with 150. I multiply those two things together, and I wind up with 15,000 square feet. So now, just like the related rates problem, I'm just going to say a sentence where I summarize everything. The optimal dimensions are W equals 150, L equals 100 feet, and the area is 15,000 square feet. And I'm going to check my answer, make sure that I answered everything. Did I answer everything? Find the dimensions for the plot that would include the most area. Hey, I didn't even need the area. I just needed the dimensions. So I made sure I answered everything. 1 to 5, how do we feel about that question overall? Okay. All right. Okay. So, let's talk about these true-false problems. So remember when I said that stuff got cut? This is what got added in its place, okay? So we had, oops, sorry about that. We had the long proof. I don't know if you're happy about that being cut or not happy, but we replaced that long proof with 5 true-false questions, which you can see on the answer key, okay? So I put on some similar types of true-false questions on this quiz. So the first one, and these can be a little tricky, and there's kind of a multi-layered way of doing this. Okay, so I mean, there's kind of you say true false. So all you have to do is say true or false. Okay, that's all that's required for the problem. But you could also give a little justification, and if you the point of the justification is if you feel so inclined, you can get partial credit. So if your justification is good on one, you can get up to half the points you missed on the whole problem, right? For, each one would be like 0.1, plus 1, up to half the points you missed on the whole problem. So if you already had a 10, you got a 10. But if you missed one, but you had one really good justification, you wind up with a 9 instead of an 8. That's kind of the idea. All right. Now, whether this idea survives the meeting tonight is another question, because they keep changing the test on me. They keep telling me to change the test. I have to do all the work, but they get to dictate what happens. And people wonder why I'm so stressed out and not making any progress on my PhD. This is why. Okay, so if f prime of u equals 0, then f has either a local maximum or a local minimum at u, and that's false. The converse is true. Right? If I had a local min and a local max, and if f prime of x existed, then f prime of x would have to be 0. Okay? But the other way is not true. Okay? So the example of this is x cubed. If we think about x cubed, right, we have this function here where the derivative here is 0 at 0, but it's not a local max or a local min. It's just kind of, up there. How do we feel about that, 1 to 5? How do we feel about part A, 1 to 5? And can you put some labels on these polls? So just like edit the poll after you type it and like put, part A, this one was part A, this one was, this one was the overall for the last one or whatever, so I can see. So we can all keep track of what the polls said. Okay. So we feel, fair about that one. All right, the second one here. Well, this one's true. Now, the way I reasoned it was this. I could either memorize the statement. It's fine. Or I could say, okay, what's going on here? F double prime of u is less than 0. So I draw a little here. That's concave down. And I've got that f prime of u equals 0. That means that right here I've got a maximum. And that's what I said, right? Then f has a local maximum at u. That is true. Okay. 1 to 5, how do we feel about part B? Okay. All right. For part C here, if f prime is greater than 0 on the interval, then f is decreasing on that interval. It's increasing. There's my line. There's my justification. That one I'm going to call false. 1 to 5. How do we feel about that? Okay. And then if d has a critical value at u, then f prime of u equals 0, or f prime of u does not exist. That's the definition of a critical value. 1 to 5 on that one. All right, this one was extremely important. if f prime of x equals g prime of x for every x, then there exists some constant c so that for every x, g of x equals f of x plus c. In other words, these things are c apart from each other everywhere. In other words, the derivative determines the shapes of the graph. Okay? They're just vertical shifts of each other. 1 to 5, how do we feel about that? That these are just vertical shifts of each other. Okay. And that's one of the major implications of the intermediate of the mean value theorem. And that's the last corollary in that section, and I proved it in class. Okay. All right. So overall for this quiz, how do we feel 1 to 5 now? Now that we've gone over it, how do we feel? Are there any questions, by the way? I'm not seeing any questions in chat. The last group was very chatty in chat, so I didn't have to ask any questions much. But I don't see any questions. I don't even see many emotes. I see someone called Thai Monster is e-voting. Jelly Sir is emailing. I don't know if these people are actually in the class or if they are. Please don't say your name, by the way, in stream chat. Well, you can't. You can only emote. Ha ha ha. But yeah. So, okay. Are there any questions? Please state any questions you have about this stuff. Okay. Oh. Is this the diagram you wanted? It's just the thing. And I'll post this. I'll post the quiz rubrics. I think I remember to post it last time. This one. Yeah, and I included the this is like what the rubric ends up looking like for these. So, and there's also a lot of partial credit here. Are there any other questions? Okay. So that is this beautiful quiz. Let's go ahead and talk about the stuff we wanted to do for today. So today we're going to do L'Hopital's rule. And if you remember from last time, if you remember from right before the quiz, the test. So we did this way back in the dark days before test 2 when we were still on campus doing live lectures. There I am. There we go. From the long dark days before class test 2, we did L'Hopital's rule. And we had this idea of the linearization, and we wanted to figure out what happens if I got 0 over 0. Okay, and we discovered that because I was doing the linearization, I could cancel those first two terms, right? They wouldn't cancel. The first two terms, f of a over the f of a term and the f of b term went away. And I wound up with this idea that all I was left with was the ratio of the derivatives. Okay, and that was L'Hopital's rule. That was the L'Hopital's rule 0 over 0 edition that we did right before. And I could only do this if it was 0 over 0. So to refresh your memory, this was, I think, the example or something similar to the example I did in class. The limit as x goes to pi of sine of pi of x minus pi. And what I'm going to do is I'm going to apply L'Hopital's rule. So I know that the derivative of the top is 0. I'm sorry, not the derivative. The limit at the top is 0, right? So I take a little unit circle there that's a little lopsided. I can actually draw a unit circle. Hold on. He's still a little lopsided. There we go. So I have a little unit circle there. and I have some, axes. Okay, my axes are off. And I went pi around. So here's pi, and the northiness of pi is 0. So the top bit is going to 0. Okay. The bottom bit, I plug in 0, and I wind up with this thing's going to 0. So L'Hopital's rule, 0 over 0 addition, says that if f of x goes to 0 and g of x goes to 0, as x goes to a, then the limit of f of x over g of x is simply the limit of the derivatives. So I'm going to do this. This is h. I'm going to put the h there to say I'm using L'Hopital's rule. That's the standard. Everyone does it. Yes, you have to do it. And I'm going to wind up with the limit as x goes to pi of d over dx sine of x over d over dx of x minus pi. Okay. Yeah. And note that I did not use the quotient rule. I took the ratio of the derivatives. I did not take the derivative of the whole thing. I took the derivative of the top separately from the derivative of the bottom. Okay. When I do that, let's evaluate these derivatives. I've got the limit as x goes to pi of cosine of x over the derivative here is 1. This is 1 minus 0, which is just 1. And then I'm going to directly substitute in, and I wind up with cosine of pi over 1, and the eastiness of pi is negative 1. How do we feel about that 1 to 5? Just a little refresher on something we haven't seen in forever. This is L'Hopital's rule. Okay. All right. So a lot of us have an idea about what was going on. All right, notice that this does not work if the limits don't go to 0, right? The limits had to go to 0. If I'm evaluating this thing, what I'm going to do, right? This goes to 1. This goes to 0 plus. So this right here equals 1 over 0 plus, and that equals positive infinity, right? This is the situation I have here. So I have this situation where here, this is the right side, this is the left side. I'm going to 0. Both sides head, as I go to 0, right, both sides shoot off to infinity. And it's different, right? So what I want to say is don't do this. What would be the derivative of that constant? Right? If I took d over dx of 1 over d over dx of x squared, what would I get? If I took the derivative of that constant, what do I get? Well, I get 0. And the derivative of the bottom would be 2x. And that would equal 0, and 0 does not equal infinity. So don't do it. Okay? How do we feel about that? 1 to 5. When I should not use L'Hopital's rule and when I should? Okay. So what I'm going to do is I'll make myself a little chart here. So let's talk about some of these indeterminate forms. So 0 over 0 is the thing that's indeterminate here. 0 over infinity, that's determined. And it equals 0 as long as the left and right exist. D&E if left and right do not exist. So remember our old 1 over x. Okay, that one was D&E, right? Because the left went one way and the right went, so the left went to the basement, the right went up here, like that, if I wanted you to see it like that. So 1 over x had this situation going on. They didn't go to the same place. Therefore, the derivative didn't exist. But it's still determined. And infinity over 0 is determined. Infinity over 0 plus is determined. That's infinity. Infinity over 0 minus, that's determined. And 0 over infinity, that is 0. How do we feel about these forms right here? That these things are determinate. They're totally unambiguous. 1 to 5. How do we feel about those being determined? All right. Okay. All right. Well, let's add to this chart. There's a question in chat. Is infinity over 0 determined because anything over 0 is always undefined? No. Infinity over 0 is determined because it's either this form or the one where this is going down like this. So in one of them, it's determined to not be existing. On the other one, it's determined to go off to positive infinity, right? So it depends if the left and the right agree. So infinity over 0 plus, which was the situation we had right here, equals infinity. Okay, and it's determined. It's unambiguous. Okay, it's a good question. Okay, it has to go, one way or the other. Whereas something that's 0 over 0 or something that's infinity over infinity could go to any number. I mean, a particular number, but any particular number. We don't know. It's indeterminate. This thing doesn't give me any information. Okay, that's the answer about that. All right, well, let's look at another one. Let's look at the infinity addition of L'Hopital's rule. Now, the infinity addition says that if f of x and g of x both go to some form of infinity, as x goes to a, then I can also apply L'Hopital's rule. There's only two things. So let's do an example here. Let's do this example right here. E to the x over x. Okay. I take here, what I'm going to do is I'm going to do, this goes off to infinity. This goes off to infinity as x goes to infinity. That means that this equals, by L'Hopital's rule, this equals the limit as x goes to infinity of d over dx of e to the x over d over dx of x. Okay. This right here then becomes e to the x. This over here becomes 1. This goes to infinity. This goes to 1. That's perfectly determined. That equals infinity. Okay. How do we feel about that one, 1 to 5? All right. So there's some big ideas to take away from this right away. I must have 0 over 0 or infinity over infinity. Nothing else works. If something is not a quotient, I put it into a quotient. And I can do this thing as many times as I want to, as long as I wind up with a finite number of times that I do it. Now, what do I mean? Are there any questions about those things? Okay. Let me give you an example then. Let's do an example of one of these. I can do as many times as I want to. Let's do e to the x over x squared. Oops, I don't want you there. Let's talk about this thing right here. Okay. Now, e to the x, that's going to go to infinity. And x squared also goes to infinity. That means I can apply L'Hopital's rule. So I wind up with the limit as x goes to infinity of d over dx e to the x over d over dx of x squared. So the derivative of the top is simply e to the x. The derivative of the bottom is 2x. How do we feel about that, 1 to 5? Okay. Are there only 3 people left actually watching me now? Okay, there's a couple more people. Please vote. Your vote matters. I sound like, Jeb Bush. Please clap. Please vote. Okay. All right. So all I did was apply L'Hopital's rule. Does anyone have any questions? I see a lot of 3s and not a lot of questions. So if someone wants to ask a question, now's the time to do it. All right. Yeah. So what do I mean by as many times as I want? Well, notice I didn't get an answer here. Okay. All I got was e to the x over 2x. Let's do it again. But this goes to infinity. And that goes to infinity. Which means by L'Hopital's rule, I got to apply L'Hopital's rule again. And I wind up with the limit as x goes to infinity of d over dx of e to the x over d over dx of 2x. Okay. Well, this right here is the limit as x goes to infinity of e to the x over 2. And then I just directly substitute in, because now I have something that's not indeterminate. And I wind up with infinity. How do we feel about that, 1 to 5? A little double application of L'Hopital's rule. Yeah. So I just keep taking the derivative. Now, I have to be able to do it in finite number of steps. Okay? So let's look at one of these. Let's look at the limit as x goes to infinity of e to the x. Why is that so thick? The limit, I don't know why it was less thick before. The limit as x goes to infinity of e to the x over x to the fifth. Now, how many times am I going to have to run L'Hopital's rule to get that answer? Yeah. Is that a 5 or a 6 there? I can't read my writing. Oh, I think it's supposed to be a fifth. What's the exponent on x? Yes, the fifth. Sorry. So yes. So if it's x to the fifth, then it's 5 times. Okay. But I can do it. Right? I'll wind up with e to the x over 5 factorial, right? 5 times 4 times 3 times 2 times 1. Which would give me infinity. All right, I'd wind up with 5 times 2 times 5 times 4 times 3 times 2 times 1 on the bottom, and I wind up with infinity on the top, which is just infinity. But the important thing was that I ran it finitely number of times. Okay? Finitely number of times. Let me show you what I mean by that. So let's look at a different one. What if I had this problem? Now, what would be the problem of associated L'Hopital's rule with this? If I take the derivative of the top, I'm going to wind up with something with a negative exponent. The exponent becomes negative 2 over 3. And the derivative of the bottom is going to become negative 1/2 is the exponent. And then I do it again, and I wind up with positive exponent. Then I do it again, and I wind up with this with either more negative exponents, or I flip them again and then take the derivative, and I wind up with negative exponents again. And this would go on forever. Okay? Here, if I applied L'Hopital's rule, I would be applying it forever. Does that make sense? I would wind up applying it forever. I can't use L'Hopital's rule here. So what I need to do is I need to do this one a different way. So now I'm back to where I was before. Right here, I've got something that I can't apply it to because I wind up doing it forever. With this one, I just saw by algebraic info. I do it just by a little algebra. Right. So while I get infinity over infinity, and then I'll wind up with 0 over 0, I can do those things. But if I keep doing it, I'm going to get nowhere. So instead, I'm just going to do a little algebra, and this is going to be the limit as x to the 1/3 minus, divided by x to the 1/2. That's going to be x to the 1/3 minus 1 over 2, which is the same thing as the limit as x goes to infinity of, let's see, this is going to be, what, 2/6. This one's going to be 3/6. So I'm going to wind up with x to the negative 1 over 6. And then when I do that, that's the same thing as the limit as x goes to infinity of 1 over x to the 1 over 6. This bit goes to infinity. This bit goes to 1. and that is going to equal 0. Okay, so those things, I don't use L'Hopital's rule for this. Use algebra ahead of time. How do we feel about that 1 to 5? I wind up with a situation where I have to do it an infinite number of times, and that just sucks, right? Finite number of times I could do it. Infinite number of times, no. All right. But the other thing I can do is I can algebraically manipulate these things a number of ways. Okay? So let's look at this one again. Here I had to use L'Hopital's rule 5 times. 5 times. Let's not do that. Is there another way to get at this? So let's look at this 5 timer. Is there another way? Yes, there is. And the other way is this, okay? So let's look at this problem again. We've got the limit as x goes to infinity of x to the fifth, e to the fifth over x to the fifth. Well, note that taking something to the fifth power is continuous. So let's do this. Let's take the fifth root of the top and the fifth root of the bottom, and then take the fifth of the whole thing. In other words, let's do this. Sorry, this should be e to the x, not e to the fifth. We're going to take the fifth root on the inside, and then we're going to take the fifth power. So I've changed nothing, right? I've just taken the fifth root of something, which is an odd power. It changes nothing. And then I've taken the fifth power. If I do this, well, look what happens. This bit right here is continuous. That means that that limit can be pulled out. The fifth can be pulled out the limit. So this here equals the limit as x goes to infinity. Now I'm going to take the fifth root of the top and the fifth root of the bottom. So I'm going to wind up with e to the x over 5 over x to the fifth root of x to the fifth, which is just x. Over x. And then take that to the fifth. Now when I do that, something very clever here happens. I'm going to move this down. All right. This bit I could use L'Hopital's rule on. So that bit, by L'Hopital's rule, equals the limit as x goes to infinity of the derivative of e to the x over 5 over the derivative of x all to the fifth. This bit here equals the limit as x goes to infinity of the derivative here. I'm going to have a chain rule, is going to be e to the x over 5 times 1/5 over 1. That is the same thing. This bit here, this bit goes to infinity. This bit goes to 1. That means that this whole thing is infinity over 1 to the 5th. And that's just infinity. So, yes, I could have done L'Hopital's rule 5 times. Or I could have done something algebraically clever and gotten out of there. 1 to 5, how do we feel about that? And I'm actually kind of bothered that there aren't any questions. People should be screaming at me right now. What the heck did you do? Maybe my audience is just not big enough. All right, so some people are lost. I'm sorry. I did a whole bunch of algebra. Okay. And by doing a whole bunch of algebra, I manipulated my way around it. All right. Let's look at some more of these. Now, I mentioned up here that I need a quotient. Okay. So let's do one without a quotient. Okay. So this one right here is example 6 in your book. Evaluate the limit as x goes to 0 from the right of x to the ln of x. So the question is, why is that easier than taking 5 factorial? It's not, but I didn't exactly write this out in a short number of steps, right? I wrote this, what I said was run L'Hopital's rule 5 times, and I'll wind up with e to the x over 5 factorial. Okay? But I didn't actually do the 5 times. Now, if it was on a test, I would accept this answer. This is great for me. I'm like, yeah, that's perfect. You know, that shows that you understand the intuition about what's going on and you apply to factorial. But that's not what they want for the, you know, that's not what the answer key is going to have as the answer. Right? Because you didn't actually do L'Hopital's rule 5 times. You just said you were going to do it 5 times. So for me, that's like, yeah. But, you know, not everybody's, you know, not everybody would like that answer. So formally, if I was going to do it, I could do it 5 times. Or I could, you know, pull the 5 out. So this is being clever. And one of the reasons I'm showing you that is because this is kind of the thing you have to do with L'Hopital's rule for a bunch of these forms. For example, so it's a good question. So let's evaluate the limit as x goes to 0 plus of x times ln of x. And this is example, oh my goodness, he's going to do an example from the book. This is example 6 in your book on page 195 in section 3.7. There's a question. Is there ever a time when I want to use the algebra version over the LH version? Yes. Okay, because a lot of times the algebra version will save you a headache, especially if you have some of these like clever ones. Remember the where you have sine. There are a bunch of them where if you do it with the where you do it with L'Hopital's rule, it just takes you forever because you have to run L'Hopital's rule 2 or 3 times. Whereas if you do it with the special limit that you proved way back in module 1, it takes like 2 seconds. So there's going to be reasons why you want to use algebra over L'Hopital's rule, and there's going to be places where you want to use L'Hopital's rule over algebra. So it's just another tool in the toolbox. It's a cool tool, but it's just a tool. Now, let's talk about this one. Here, if I do this, this is going to be 0. This right here is going to go to 0. This right here is going to go to infinity. And 0 times infinity is another one of those indeterminate forms. Okay. Matter of fact, let's go add that to our thing above. Okay. This idea that 0 over 0 is also indeterminate. Let's go ahead and add that to our big chart up here. Yeah. Now, the question is, how do I manipulate this problem so that it's back in the form I want it to be? I need to manipulate this because I want this to either be 0 over 0 or infinity over infinity. Okay. There are a couple ways to do it. I could put the x as a 1 over x on the bottom, or I could put the ln of x as a 1 over ln of x on the bottom. Okay. The point is I need to get something so that it looks like a quotient. So what I'm going to do is I'm going to say, okay, I'm going to do a little algebra here. This is going to say that the limit as x goes to 0 from the right, I'm going to make this ln of x over x to the negative 1. Now, why can I do that? If I have 1 over 1 over 3, what does that equal to? Well, that's 1 divided by 1 over 3. Is everyone on board with that? Which, if you remember from grade school, is the same thing as 1 times 3, which equals 3. So what I'm going to do is I'm going to go backwards here. I'm going to start here with x. And that's the same thing as 1 times x. And that's the exact same thing as 1 divided by 1 over x. And that is the exact same thing as 1 over x, which is the exact same thing as 1 over x to the negative 1. How do we feel about that conversion, 1 to 5? One to 5, how do we feel about that? Okay. It's a fancy little dancy piece of algebra. And it's not something you normally think about. Coming back to this. All right, so the log of x, as I go to 0 from the right, this thing goes to, I don't want to use that color. That color's ugly. This thing right here goes to negative infinity, right? Because log looks like this. One to 5, how do we feel about that? That's where that log of x is going. It's going to negative infinity. As I go to 0, the log goes to negative infinity. Okay. This bottom bit here, well, as I go to 0, this goes to positive infinity. X to the negative 1. Whatever x goes to positive infinity as I go to 0. Right? It looks like this. Right? So as I go to 0 from the right, I wind up at infinity. Okay. That means I could apply L'Hopital's rule. I've got something infinite. Oops, wrong mouse. I have something infinite over something infinite. This was a negative infinity, but it's still something infinite over something infinite. Okay. That means that I could apply L'Hopital's rule. And I wind up with the limit as x goes to 0 plus of d over dx of ln of x over d over dx of x to the negative 1. All right. So let's do the calculus. And I wind up with the limit as x goes to 0 plus of 1 over x over negative 1 x to the negative second. Now what I'm going to do is do the algebra. I'm going to move the top to the, I'm going to move this negative 2 to the top. I'm going to move that 1 over x to the bottom as a positive 1. And I wind up with the limit as x goes to 0 plus of, remember this right here is the same thing as x to the negative 1. So I'm just going to move everything around, and I'm going to wind up with negative x squared over x, which is the same thing as the limit as x goes to 0 of that cancels this right here 1. This bit right here cancels with that whole thing there, and I wind up with negative x over 1. I lost my plus, and that I just direct sub in, and that equals 0. How do we feel about that, 1 to 5? Okay. All right. So we're a little confused on this. This is a lot of algebra. But the whole point is that I can wind up manipulating. I take these things that are products and I wind up manipulating them. And I could do the exact same thing with exponents. How much time do I have? Ooh, I might even make it. Let's do an indeterminate power. This one right here is one of the examples in your book as well. Apparently, I read research that said I'm supposed to do examples from the book when I'm teaching remotely. So I'm trying to do that. Believe it or not, I actually care about how I do this remotely. I actually care about the result, which is you learning calculus. So I looked up the research. Heaven forbid. Let's do a determinate power. This is example 9 in your book. And there's a similar one on the and there's a similar one on the bootleg. This is the indeterminate power version. So this right here is consider the limit as x goes to, let's see, what did they use? 0 plus of x to the x. So this is this function x to the x, and you've seen it before, and I put on the bootleg, I put the x root of x, which is the same thing as x to the whatever x. And here we're going to get back involved with logs, okay? So here what I'm going to do, 0 to the 0, by the way, is another one of our indeterminate forms. Okay, so here what I'm going to do is I'm going to wind up manipulating this a little bit. Okay, now recall that exp and ln are inverses of each other. In other words, the exp of ln of x equals x. Right, and remember also that exp of x is the same thing as e to the x. Okay? So just remember these things from the past. Are there any questions? I haven't seen any questions in chats in a while. I've seen some thumbs up. I've seen some emotes. Okay. There we go. All right. So 0 over 0 is one of these indeterminate things. 0 to the 0. So what I'm going to do is I'm going to manipulate this with a little algebra. Okay. I'm going to do this. I'm going to say this equals. Now, I'm going to take the exponential of the log. Okay. Now, since exp is continuous, I could pull out the exp. So this becomes exp of the limit as x goes to 0 from the right of ln of x to the x. Now, what was the whole point of doing that? Nobody wants to type in chat what the whole point of doing that was? You're hurting my feelings. All right, some people are typing. To pull the x in front, exactly. The whole point of doing that was to get the x out front. Now, with the x up front, I can apply L'Hopital's rule, right? I can do the manipulation where I stick this on the bottom. I'll get 0 over 0. I'll get infinity, negative infinity over infinity. But hey, look, that was the problem that I just did, right? That is this bit right here. I just did that problem. And because I just did that problem, I'm not going to do it again. Okay? So that equals exp. I already know that this limit is 0. And so that whole thing is 1. 1 to 5, how do we feel about that? That one's hard. And I'm 2 minutes over. I know that because that was the problem I just did, right? This problem right here is the same thing as this problem. These are the exact same problem. Okay, so those are the exact same problem. So I knew what that was, and I just said, okay, I know what that is. Okay, the reason I could pull out the exp is because exp is continuous. Remember that right? That was the definition of continuity. If f is continuous, then the limit as x goes to a of f of x equals f of a. But that's the exact same thing as saying the following. That's the exact same thing as saying f of the limit as x goes to a of x. Because this thing right here equals that thing, right? This part here equals a. So f of a, I can rewrite f of a as that. Okay, those are two equivalent statements. So I have, if f is continuous, the limit as x goes to a of f of g of x equals f of the limit as x goes to a of g of x. Okay. The theorem you can refer to is simply the definition of continuity. You know that exp is continuous. Okay, the exponential is a continuous. E to the x is a continuous function. Okay, so if you want a theorem, it's just that e to the x is continuous, right? So that's what I wrote here. Since exp is continuous, right, that I can pull it across the limit because that's the definition of continuity. Continuity means that the thing equals the f of the limit of f of x equals f of the limit of x, which is the same thing as a. 1 to 5, how do you feel about that one? Okay. Are there any questions for me? Comments, issues, suggestions, thoughts, hate mail? Okay, I see some ones. I see some twos. I will be happy to talk to you about them if you wish. But that's it for the class. So I'm out of time. So for today, and I'll talk to you about it. I'll talk in Discord chat in just a moment about this thing again. But for today, what we did was L'Hopital's rule. Remember the things. Remember the big things. I must have 0 over 0 or infinity over infinity. Nothing else works. If I don't have a quotient, I need a quotient. If I can do it as many times as I want, as long as it's finite. Okay, so those are the 3 things to remember for this. On Tuesday, tomorrow, I will do a part 2 of optimization, totally optional. I will be answering one question through the problem set all the way through. You're welcome to watch the video and follow along with the video to do it. You're welcome to do it any way you want to. And then on class on Wednesday, we will do the max function, and then we will talk about, we'll start module 4. And the max function is technically part of module 3, but no one ever does it except me. So I do it right before I do module 4 because it's not on the test. But it is important to kind of understand module 4. It's kind of one of these first times when we see a parameter floating around for a function. Are there any other questions for me? Comments, issues, suggestions, thoughts? Okay. I see people so in chat, so I'm going to stop streaming and I will speak to you about it in Discord.